So I'd like you to actually say, I understand what you're talking about when you say the mole. Now, maybe it didn't happen yesterday, but maybe it'll happen today. Well, let me go back and let me tell you that if you think about chemistry, the history of chemistry, remember that video you saw and they discovered, hey, here's a gas that does this. It puts out a flame. Here's a gas that makes a flame brighter. Here's a, and they didn't know exactly what that was. Yes, now, today we do. You did the experiment, didn't you actually produce oxygen gas? And didn't you take a glowing wood splint? I mean, you did that kind of stuff. But we actually now know what's going on. But how did we know that? How did we figure that out? And it had a lot to do with figuring out how many atoms combine with how many atoms. So we knew there were elements, and eventually they were finding new elements, and I got that. There's my building blocks. But most of the world is not just pure elements, is it? Isn't most of the world compounds? Or maybe mixtures, that kind of thing? So the next step in chemistry was, I've got to figure out how many of these combine with how many of those. And then we had these things called formulas, right? How do they do that? How do they do that? Can they visit that little tiny world and look and find out, oh, I see, there's 1, 2, 3 carbon. Is that it? We can't do that. It's too small. And can we count, if I give you a handful of sugar, here, count the carbon atoms in a handful of sugar. I can't. There's too many. And so that was a big problem. You might say, oh, let's go home. We can't do it. We're done with chemistry. We can't go any further. Well, they didn't. And that's where I think God gave us this mind. He didn't give us the answers. You got that? That was interesting. He could have loaded all the answers into your brain. And we'd be doing all kinds of stuff. But he gave us a brain to ask questions, but we had to come up with the questions, didn't we? And we had some questions we thought we answered one way, and they were wrong. We went back and fixed them. And that seems like that's part of the human condition. We seem to do that a lot. So how in the world do we find out how many are in water? They didn't know that one time. They didn't know water was 2 H's and an O. So how did they do that? So let me show you the connection again. If I were to visit the tiny world of atoms or molecules, okay, and I can't go visit that world, but I can think about it. And I said, let's talk about one water molecule, just one molecule of water. Now, we know today that's made of 2 H's and an O. We also know that over a long period of time, we eventually figured out these numbers here. Not the 1, 2, 3, 4, 5. That has to do with the nucleus and protons. You get that? And if you're a neutral atom, it tells you electrons. But here's this other number, this decimal number. And we did this on another chapter where I said, why is that not a whole number? What's that I word, and don't say ions this time. What's the I word is why this is not a whole number? Isotopes. So we eventually developed a machine, a mass spectrometer, that you could load in 1 million atoms of oxygen. And it'll actually, yes, it's a $500,000 machine. Yeah, it's a lot, $250,000 probably now. But it can actually separate the isotopes and give you a count. Hey, 15% of them are this mass and 85% of them are this mass. And then, so what happens is, in chemistry, if I'm going to use oxygen, I can't say, hey, I only want oxygen 16. Come here. What are you going to do with the ones that aren't oxygen 16? They're going to come along with the ride, aren't they? Here's a piece of copper. Hey, tell me, what's the mass of every atom on there, huh? Well, the periodic table says, well, what is it? It's maybe there are some 65s, maybe there's some maybe there's 63s, maybe there's 64s. I don't memorize all the isotopes, but we know that on the average, what mass does that copper have? This guy, see that? But there are no copper atoms of that mass. That's like the jelly bean thing, isn't it? So eventually, these numbers, I needed to know an average number for the mass of one of those kind of copper jelly beans. You get it? So no jelly beans at this mass. No copper jelly beans. But if you gave me a chunk of copper, they're in there. There's some 63s in there and 64s. And we can't, it would cost a lot of money to separate into individual isotopes and then do an experiment. We're not doing that. Got that? So let's go down. Let's pretend that these both have a mass of 1 AMU apiece. And I know that almost all the hydrogen isotopes have a mass of 1 because look at the average. There are 3 kinds of hydrogen isotopes, aren't there? Why would the average be so close to 1? Because I bet almost all of them have a mass of 1, don't they? Okay. So you have let's say this one happens to have a mass of 1, you have a mass of 1, you have a mass of 16. In the little world, what would the molecular mass be? 18 what? What units would you use? Don't say grams. Not in the little world. AMUs, right? Now, what if I give you 100 hydrogens? 100 waters, I'm sorry. Instead of being 18 AMUs, it would be 18 times 100, or 1,800 AMUs. Okay. What if I give you 1,000,000 waters? Well, then that's going to be how much? That's going to be 18 million AMUs. Is that right? Now I'm going to give you something way more than 1,000,000, way more than 1 billion, way more than 1 billion billion. I'm going to give you this many. Whoa, that's a funny number to pick. It is. It is a funny number, isn't it? If I give you 6.02 times 10 to the 23rd, it'll be a huge, huge number of AMUs, won't it? It'll be 6.02 times 10 to the 23rd times 18 AMUs, right? Woo! That's going to be a lot of minute. But the good news, what else does it equal? If I give you this many water molecules, it'll be a huge number of AMUs, but guess what it equals in grams? And that's what's amazing. What is it? Raise your hand if you know. Uh-oh. Oh, Elizabeth, what is it?
18 grams.
Yes. Yes. Everybody got that? That's great. Okay, see that? So now, watch one more time. So this number here has 2 bits of information. In the little world, what's the mass of 1 carbon atom? Let's go ahead and say that the most common one is 12, okay? What's the mass of 1 carbon atom? 1. What is it? 12 what? Yes, 12 AMUs. Get it? What if I give you, though, I give you a whole lot of carbons. I'm going to give you 6.02 times 10 to the 23rd. I'm going to give you a mole of carbon atoms. That's a lot of them. What's the mass of a mole of carbon atoms?
12 grams.
What is it?
12 grams.
12 grams. And you know what? This is so fantastic because I can't visit the little world of AMUs, but if you tell me, if I go get 18 grams of water and I got to put that in a beaker or something, you know what's in there? Besides 18 grams of water, what is it? 6.02 times 10 to the 23rd water molecules. What? That's right. And this is called the molecular mass because that's 1 molecule. That's in AMUs, right? This is called the molar mass. Now, what do you think molar mass is? You'll hear me say molar mass over 100 times this year. What do you think the molar mass means? I bet you can figure it out. What do you think the definition of molar mass means? Say the word loud. Now, how many moles? The molar mass. It's the mass. Weight, okay, the mass in grams of how much? You know, that's your last name. Yes. So, what is molar mass? It's the mass in grams of what? 1 mole of you. Let's try it again. Look over here. What was the molar mass of sodium? What's the molar mass of sodium? If I had pure sodium here, and I gave you 6.02 times 10 to the 23rd atoms of sodium, what would the mass of that mole of sodium be? What's the molar mass of sodium? 23 what? Grams. When I'm talking about moles, I'm in the big world. When I'm talking about 1 molecule, I'm in the little world, aren't I? One more time. What's the mass of one sodium atom in the little world? Everybody. Uh-oh. I don't want to lose you here. What's the mass of one sodium atom? And I'm in the little world, aren't I? How much is it? 23 what? AMUs. But what if I give you a lot of sodium atoms? I mean a lot. Like 6.02 times 10 to the 23rd. If I give you a mole of sodium atoms, how much does that weigh? How much? 23 grams. I'm looking at your faces. That's the only way I can tell if you're getting this. And so, wow, this is pretty neat. When we discovered the mole concept, it's almost like, hey, whatever's going on in the little world of AMUs that you can't visit, if you can magnify it in the mole world, and we can do experiments. Can I do experiments with 23 grams of sodium? I can put it on a balance, 23 grams. Hey, how many atoms are in that 23 grams? How many? If I put 23 grams of sodium on a balance, how many atoms are on that balance? 6.02 times 10 to the 23rd. And now, you see, that's going to unleash chemistry, saying now I can figure out how many atoms there are. And I'm going to count those atoms, not by counting, but by what? By weighing them. Using the mole concept and weighing them. Remember the jelly beans? I'm not counting 1,000 jelly beans. I'm going to weigh them, right? And divide by what I think is a good number for the mass of one jelly bean, right? All right, you okay with that? Now, as we keep going, I don't want you to walk out and say, I don't know what a mole is. Right? If somebody says, hey, what's a dozen? How much does a dozen weigh? What would you say? How much does a dozen weigh? You say, a dozen what? A dozen cars? A dozen sand grains? I can't tell you how much it weighs unless you tell me what it is, right? So watch this. How much does a mole of sodium weigh? I can tell you that. Hey, how much does a mole weigh? What should you say? How much does a mole weigh? What should you say? A mole of what? But what is it that a dozen baseballs and a dozen donuts and a dozen pencils, what do they all have in common? It's not mass. What is it? Somebody said it. The number of particles. The mole is not mass. Look at me. Mole is not mass. Mole is number of particles. You get it? Yes? All right. So, now what I want to do is, we did this thing early in the year, and it was factor label. Remember that? Well, your buddy's coming back. So we're going to be using factor label a lot. And factor label is a great tool. It's a great thinking tool. But the key is having these things called equivalents. Isn't that right? We need equivalents. So this will be a sheet that you'll use, or, I'll have you write it down today. But eventually some of you are going to say, I think I get this. I think I get this. So let's try it. Let's do the mole concept. And I'm going to call them equivalents. And this will be the key for you doing almost any kind of mole problem. You got that? Now, we have other kinds of problems besides mole problems, but this is what we're going to spend a lot of time with these. So, first of all, number one, what if we're talking about just elements? So, for elements. All right, here we go. I'm going to start out. Your first example is, I'm going to say 1 mole, and I'm going to pick an element. Okay, I think I'll pick carbon. Okay, 1 mole of carbon equals, it equals this. It equals 6.02 times 10 to the 23rd. Now, watch this now. What's the smallest part of what's the name of the smallest particle of an element that still acts like carbon? What is it? Atom. Now, believe it or not, what you put, and I don't want you to just put atoms of carbon, okay? When we start getting stoichiometry, your labels are going to make a huge difference for you. So don't get lazy on me and say, I'm just going to put that number. I'm not going to put a label. Don't do that. All right, now we're not done. and that's true. We have one more thing, and we're going to get into a thing called molar mass. Molar mass means what's the mass of a mole of that stuff? And that's going to be in grams, isn't that right? So tell me that. What's the mass of 1 mole of carbon atoms? And we're going to say about 12 grams, okay? Is that right? So that's about, and I like to use 3 sig figs. So even if I look up there, I'm going to use 12.0, okay? So if I use 3 sig figs, I'll say 12.0. Is that pretty hard? All right, you do one. You do one. 1 mole of uranium. You do that one. 1 mole of uranium. Go ahead and finish the equivalents. Hopefully you've already gotten this part done. And you put atoms of uranium. And then what? What'd you put, Kayla? What'd you put on the third? Okay, you know where I got that number? I'm going to put that right here. You know where I got that number? From the periodic table. So I'm going to put a little note here, because if at least one person wasn't sure, then maybe I should make sure you said that. What do you have, Ethan?
I had 238 grams.
Of uranium, right?
Yeah.
Everybody get that? So you'll always have a periodic table in all the tests. You get that? You'll always have a periodic table. Let's see. Let's do one more. If you get this one right, we'll move on. Okay, 1 mole of sodium. Again, you guys have a bunch of periodic tables I gave you. You also have one in your book. Now, by the way, you know what I'm really doing. You don't know what I'm really doing. What I'm really doing is, by the time you do this the third time, do you know what? You won't need this piece of paper. By the time you do this again, you'll say, what do you want to do? Sodium? Okay. 1 mole of sodium equals 6.02 times 10 to the 23rd atoms of sodium equals what? And I go over there, and I'm going to round up to 3 sig figs, 23 grams of sodium. So again, I know a lot of times in school you say, well, I better hang on to these notes. Those notes, I better memorize this page. What's going on? What are you going to memorize? What you need to do is say, oh, I understand how to do that now. And let's pretend like I don't have this paper with me, all right? Let's pick lithium. 1 mole of lithium. I always start with 1 mole, don't I? 1 mole of lithium equals, without looking, can you tell me? What do you think, Jonathan? 1 mole of lithium, help me out, equals?
6.02 times 10 to the 23rd atoms.
Yes, equals? Okay, 7 grams of lithium. Are you okay? I'm okay to write these down, but by now I think I could do this without that paper. Now, I want to go ahead. I'm going to draw a line here because there are other things besides elements, aren't there? And you can still use a mole concept for those. So let's do molecules, which means they're covalent compounds. Covalent compounds. And covalent compounds are always what? Aren't they non-metal? What are covalent compounds? Non-metal, non-metal. Okay, so let's get an example. Hey, water. Yeah, water. Okay, let's do water. Don't go to sleep too often. Okay. All right, ready? 1 mole of water equals, all right, go ahead and do that. See if you can do it without me, without my help. And remember, factor label, the label is just as important as the number. So you got to have a label on all these. This would be interesting to see what you put here. Now, if you put atoms of water, that means all you're doing is mimicking. You're mimicking, you're not thinking. You know how I know there's no such thing as an atom of water? How do I know there's no such thing as an atom of water? That's the only atoms I know. You see water up there? There is no such thing as an atom of water. Hey, atoms of air? No. Skin? No. Plastic? No. Wood? No. Pimples? No. If it's not on the periodic table, there's no such thing as an atom of it. But some of you might put atom here and said, why? Could you put atom here? Well, what's the smallest piece of an element that acts like that element? That's an atom. What's the smallest piece of a covalent compound? What's the smallest piece of water that acts like water? Molecule. You got that? Say, wow, that makes sense now. Now, what are you going to do about the molar mass? What are you going to do about the molar mass here? What do you think? Who have I called on? Danielle, what's the molar mass of water?
Oh, it'd be
18
18 grams.
what? Yes. Okay? Because each of these weigh, a mole of hydrogen weighs 1 gram, and I have 2 of those. 2 moles of hydrogen would weigh 2 grams, and 16 grams. So you get 2 plus 16, it gives you 18. Now you're going to do this a lot in here. You have to figure out the molar mass of different chemicals like that, like sodium nitrate. What's the molar mass? We'll do that in a minute. Let's do another one. Try this one. 1 mole, and remember this is a non-metal. Okay, carbon dioxide. Go ahead and do that. All right. Tyler, ready? 1 mole of carbon dioxide equals what? Equals how much? Yes. Oh, man. You guys are catching on. See, once I give you the keys, these are like the keys of factor label in the mole concept. These keys will open up any door you want in the mole concept. I'm going to give you one that's kind of unusual. Okay? Even though we say it's an element, it's one of those special elements. It's a diatomic element. Let's do this one. So this was a little bit unusual because we call it an element. We call it a diatomic element, but isn't it really a compound? Isn't O2 really a compound? And isn't it a nonmetal and a nonmetal bonded together? And Davis, what do you think here? It's kind of a tricky one. Maybe. Maybe not. Nice, very nice. So it'd be 2 oxygens together would be 32, wouldn't it? Wow, you guys are doing well. You guys are doing well. Okay, let's do one more. Let's do that. Now, I doubt whether I asked you to start reading the chapter, but I doubt whether you read this far. So I don't know if anybody in here would actually get this right, but I do want you to keep reading the chapter. Got that? So keep reading the chapter. Let's see. Actually, you want to tackle it? You want to try it? I actually don't think anybody will get it right, but you know what? If nobody can get it right, you have nothing to lose. So what do you think here?
It's the 6.02 times 10 to 23. Is it compounds?
It could have been. It could have been. So we're going to leave that blank, and I'll tell you what that is in just a minute. What about this other part? And by the way, I might as well tell you right now that I don't mind if 18.99, 3 sig figs, that's 19, isn't it? I don't mind using 19 for fluorine, but what are you going to use for chlorine? Do not tell me it's 35. If you use 3 sig figs, you get 35 point what? 35.5. Don't use 35 for chlorine, use 35.5. And look over here, look at copper, 63.546. You can't use 63 for copper. That's 63.5, isn't it? So if you just round them to 3 sig figs, I'll be really happy. What do you got, Max?
59 grams.
Wait, 35.5. What did you use for sodium?
23.
23? 23, right? So what's 23 and 35.5?
Oh, I rounded up.
No. We'll stay with our 3 sig figs, okay? Is that all right? Everybody got that? Now, the mystery is right here. Now, if we could go back in time and I was the emperor of the universe, I would have told him to change all the chemistry books and said, hey, you know what's different about NaCl? NaCl is really different than these guys here. These guys up here, there really is a hydrogen atom bonded to an oxygen, bonded to a hydrogen, and it takes all three of you to make one water molecule, doesn't it? So you got to have all three to make a water molecule. But what about this stuff? They doesn't have a covalent bond. But in fact, the only reason they stay together is what? What are they made of? What's the only reason ionic compounds stay together? What? It's much different than a covalent bond. Covalent bonds say we're sharing each other's electrons. There's no sharing going on here. So why do they stay together? Somebody said it. I know, but what's the nature of an ionic bond? Why do they stay together? We had this many chapters ago. What is it? The attraction between what and what? Positive and negative. That's why they can't get away from each other. They're not sharing anything. See, how do you become ions anyway? Oh, I lost an electron. Oh, yeah, I gained it. I became a positive ion. You became a negative. What? Hey, you can't get away from each other. That's much different than a covalent bond. So if I was a universe, the emperor of the universe, I would have said, go change every chemistry book, and I'm going to call this one ionic unit. I like that. Because an NaCl is an ionic unit. You get it? It's a unit of ions, all right? It's the lowest ratio. It's 1-to-1. It's an ionic unit. Okay. Somebody a long time ago had another name, and I can't get rid of it. I'll tell you why I don't like it. Because first of all, it takes a lot of time to write it out, and I don't like writing the abbreviations. But anyway, we'll do it anyway. Formula units. Okay. Now, I know because you're in 10th grade, you're going to say, abbreviation? I'm going to do that. Okay, but anyway, so I wish they had IU, like ionic units, but they have, okay. So anyway, the only real difference here is what do they call the smallest piece of an ionic compound? They call it a formula unit. That's the only difference. You get it? What's the smallest piece of an element? We call it an atom. What's the smallest piece of a covalent compound? We call it a molecule. And what's the smallest piece of an ionic compound? A formula unit. Okay? Yes, if I could go back and fix it, I think ionic unit makes a lot more sense. You can do one more, okay? Let me give you a hard one. Ooh, let me give you a hard one. Ooh, here's a hard one. 1 mole of barium nitrate. Well, if you can get this one right, you are way ahead of the game. Yeah, if you don't have your calculator right now, you probably, I mean, maybe you're pretty good at adding things in your head. Maybe. Is everybody okay with that? Has everybody got this part done? Okay, now you're just doing the molar mass. Is that what you're doing? So you got your calculator out, and you're going to do this a lot in chemistry. Here we go. Barium, let's find you. I can't read it. 137.3. How many nitrogens do you have? Be careful. How many nitrogens? 2 times 1. So what are you going to add to it? 28. Is that right? You're going to add 28. And then how many oxygens? 6. 6 times 16. Everybody get that? What's 6 times 16? What is it? 96. Okay. So what's the total? One more time. 261. Is that what everybody's getting? If more, okay, good. Wow. Okay. You guys are very advanced now. You already know how to do the molar mass of barium nitrate. What I'd like to do in the remaining time, have a little bit of time here, I'm going to pick a random mole problem. One that might be doing in college right now, or one that you should be able to do a week from now, or even 2 days from now, okay? I'm going to pick a random problem, and let's see how well you do, okay? 1 gram of water equals how many molecules of water? Okay, and then the second problem, and I want you to show me your factor label work here, okay? And the second problem is 1 gram of water equals how many moles of water? Okay, so do your factor label, and you guys, do you need a little refresher course on factor label? Is it okay if can I do it? Can I do one for you? Okay, let's do a refresher course on factor label. You always put the given first. 1 gram of H2O. And since all of that's in the numerator, I'm just going to go like that. Okay. Now I'm going to multiply by a conversion factor. Conversion factors are made of, starts with an E. Conversion factors are made of equivalents. Where do you find equivalents for water? Here we go. There we go. There's your 3 equivalents. Now, which ones do I know? Which ones do I need? There's the easy part. What label has to go away? Grams of water has to go away. What would you like to replace it with? Oh, how about that? Okay, let's do it. Now, where am I getting these numbers again? From equivalents, right? So let's go back up here. Tell me how many grams of water equals how many molecules? Just a minute. I'll go up here. No. There he is. Yeah, grams. 18 grams. Put that down there. And what do you see for molecules? No, yes. Okay. Wow. Wait a minute. You didn't use this. You didn't use this. Maybe I'll use it tomorrow. I don't need to use it for this problem, do I? Do I need to use the 1 mole of water? I'm not going to use it today. All right. Now, are you okay with this? Do you remember how to use a calculator? Okay, 6.02 times 10 to the 23rd, and then you say divided by 18. And the only unit left is molecules of water. Let's see, 1 gram of water, that's not very much. That's like 1 milliliter. How many molecules are in that thing? All right, instead of saying it out loud, as soon as you think you have the answer, find the person sitting closest to you and compare your answer to their answer. 1 gram of water equals how many molecules? Now, if you don't match, wait a minute, if you don't match, go back and say, what did I do wrong? What did I do wrong? All right. Ty, did you match? Did you match? Okay, well, tell me what the answer is.
3.34 times
10 to the 22nd? That is a lot of molecules, isn't it? That's a lot. All right, one more and you're done. All right, ready? All right, one more. Wait, what time is class over? Now? Okay. All right, see you later. Wait. Oh, 10 after. All right, sorry. Okay. All right, if you do one more problem, I'll stop, okay? 1 gram of water equals how many moles of water? 1 gram of water equals how many moles of water? And you just kind of, what label has to go away again? Okay. That label has to go away, doesn't it? That has to go away. What do you want to replace it with? Now, you know, every year, here's what people do. You know what it is. 18 grams of water is equal to how many moles? And every year, I can look up here, how many moles of water is that? Look, how many, 18 grams of water is how many moles? But every year, people say, I got to use 6.02 times 10 to the 23rd. Why would you do that on this problem? This problem, 1 mole of water, isn't it? 1 mole of water is 18 grams, isn't it? All right, so. Who have I not called on yet? No, Ramos. I haven't called on you yet. What do you got? Do you have this one done or not? Okay. John, do you have it done?
No.
Okay. No, Wood, you got this done?
No.
Okay. Sorry. Carolyn, what do you got? One more time. I can't hear. Let's do scientific notation. Does everybody remember how to do scientific notation? You put mode, scientific. Everybody do that? If the number's like 16 or 0.1, I'm okay. But you start doing 0.000 or something like that, we need to start using scientific notation. What do you got? 10 to the negative what? 2. And what's your label? That's right. Now, if you saw somebody, your brother or sister, your cousin, or friend who's taking college chemistry right now, and they say, "Oh, we're doing this mole stuff," you should be able to do these kind of problems. If it's just converting from one unit to another, you should be able to. If they don't know how to do it, you can teach it to them. Got that? All right, you did a great job today, and again, congratulations on the test. You did a good job on that. Guess that's it's gonna be nice today, but not tomorrow. Tomorrow's not gonna be so nice. High tomorrow's only gonna be around 40. A little bit of rain, but enjoy today.
It's a good day for Tom and Jerry.
Hopefully you got to go outside yesterday. Enjoy that.
It's a good day for golf.
All right, good. Who's golf? Who's golfers?
Me, Ty, John, and Kyle.
Wait, what? You? All right. And who? John?
John and Kyle.
Really?
Yep.
Which Kyle though?
Kyle Sampson.
Oh, really? So all the 10th graders, our whole golf team, 10th graders?
No, and then it's like a bunch of freshmen. And then I think
No juniors or seniors?
I think
one junior.
yeah, who is it? Eli?
Yeah.
Eli Holmes.
Okay.
So yeah, we have a young team.
Wow, man, if you guys, that's great.
Yeah.
What got you started with golf?
Hmm?
What got you started with golf?
I don't know. I've been playing golf with my dad.
Oh, good. Excellent.
Me and John just been getting lessons. We
You
just
know,
played-
lessons definitely help.
Yeah, we played a lot over quarantine in the summer. All of us together, we're like, might as well just try out for the team. And
Nice.
we made it, so
Nice.
Yeah.
Now, is Mr. Wait a minute, I see his face.
O'Brien.
O'Brien, yeah, sorry. I should have told him his name. I was gonna say Paul, you don't, I must have thought. Yeah, he's bye. He seems to enjoy
Yeah.
doing the golf, and I like him. You can tell he talks kind of like he's I guess from Kernersville, but
Yeah.
but I like that.
Yeah.
So,
Yeah, but I mean, I was like, I get to play, 9 holes of golf for free at the country club for
What,
practice.
at the country club?
Yeah. We play at the country club at the
Man.
farm course up there.
Yeah,
We
for
play
free.
Today we're at Greensboro National, so I mean,
Yeah, man, oh man,
Yeah.
that costs a lot of money.
yeah, I know.
Yeah.
It's it's real.
What a great deal.
Yeah.
All right, I hope you guys do well.
Thank you.
Oh, I should have turned that off.